Okay, so for this proof, I'm going to establish that when I take the derivative of a function x raised to n, where n is an integer, that its derivative is that integer times x times n minus 1. So an example of this may be if I had the function x squared, its derivative should look like, well, n is 2, so I'm going to multiply that. And then it tells me to subtract 1 from n, so I'll end up with the derivative of f of x equals 2x is simply 2x. Now, before I do this proof, though, I need to bring in a little tool here. So I'm going to need this property here, and this works as long as n is an integer. X to any integer minus a constant raised to any integer factors out like this. Now, we could multiply this all the way out and show it step by step. It's a bit of work, so I'm just going to give you an example of this. So let's take a look at x to the fourth minus a to the fourth. So if I had something like that, I should be able to factor it to look like this. I cubed plus ax squared, because my n minus 1, if n is 4, 4 minus 1, I'm sorry, this should be a 2 here. Little mistake. Sorry about that. A 2. Sorry. So, 4 minus 2 is 2 plus a squared times x. Again, I keep subtracting 1 from the exponents on x. I keep adding 1 to the exponents on a until I get my full pattern out, and the largest exponent should be 1 smaller than the original left-hand side. Now, if you were to distribute this out item by item, you would see that when I distribute the x out first, let me color code that, I get x to the fourth plus ax cubed plus a squared x squared plus a cubed x. And then when I distribute the a out, I get negative ax cubed minus a squared x squared minus a cubed x minus a to the fourth. Notice when I add these together, or combine all like terms, I just lined up my like terms, I end up with x to the fourth minus a to the fourth. So again, I'm just showing you that this property works, and I can factor anything that has integer exponents into this. Okay, so let's talk about how this is going to help me establish my proof as long as x is an integer exponent. So, to take the derivative, let's change the color here of my, well, that's fine. To take the derivative of x to the n, I'm going to use the limit as x goes to a of, first thing I'm going to have is f of x plus a. Hang on just one second. And so if I have, I'm sorry, it's going to be f of x minus f of a, the technique I'm going to use. So f of x is x to the n minus f of a, which is a to the n all over x minus a. Now, I need to simplify this. And what I can do now is take my top, and I'm going to use this set here, and I'm going to factor it out, and I'm going to write it just like that. Oops. So this is going to equal minus a times x to the n minus 1 plus a x to the n minus 2, and I'm going to keep adding my pattern together until I get to a to the n minus 2 times x plus a to the n minus 1. That is my numerator factored out all over my denominator, x minus a. And now I can reduce my fraction and I'm just going to rewrite this. What's really important here at this point is to recognize how many terms I have. And there are actually n terms in this pattern. This is important because we don't see each and every single one of them, but how do I know that there are n terms? Because my exponent's going down by 1, then down by 2, then down by 3, 4, 5, 6, and when I get down to here, I've actually removed n minus 1 of them, so that's 1 less than n. One more term is n terms. So that's important because at this point I can do direct substitution. So everywhere now that I see x, I can replace it with an a, which gives me a to the n minus 1 plus a times a to the n minus 2, and the pattern continues to a to the n minus 2 times a plus a to the n minus 1. And don't need to do anything to the first one. Notice what happens here is I add my exponents together when I'm multiplying like bases. So n minus 2 plus 1 gives me n minus 1. And that's going to be the same over here. Add my exponents, I get a to the n minus 1. So all I have is a whole bunch of a to the n minus 1s. I'm going to add them together. I need to know how many there are, and we already talked about that earlier. There are n of them. So if there were 4 of them, then my answer would be 4 times that. If it was 5 of them, it would be 5 times that. In this case, there are n of them times a to the n minus 1. So again, my derivative of x to the n gives me this pattern here, which can be summarized when x is a. So that is the proof of the power rule when my exponent is an integer. Now, unfortunately, establishing this for anything but an integer is a little bit difficult. Though it actually works whether it's an integer or not. It's just the proof of that is beyond the scope of this class. So I was able to power rule for integer exponents.